All right, in our lesson video today for 6.4, we're going to be taking a look at segment relationships created with these different segments when we have circles. So this time we're not focusing on arcs and angles like we did in the last few lessons, but now we're focusing on segment relationships. And there's some formulas we're going to look at for this. All right, so as we look at lesson 6.4, there's a lot of different segments that intersect circles. And in fact, I'm going to take you back to the very beginning where we talked about these different segments, okay? Obviously, we have center, radius, diameter, those things, but we're focusing on chords, tangents, and secants today, okay? Chords, tangents, and secants are those words we're going to use, okay? Remember, a chord is a segment that intersects a circle where both endpoints are on the circle. A tangent is a line, segment, or ray, anything where any kind of line or portion of a line that only touches a circle at one point. And a secant is a line that intersects a circle and has part inside and part outside, okay? Because it crosses the circle at 2 points and it goes inside and outside. All right, so let's look at today's lesson then, 6.4. All right, the first relationship we're gonna look at is when I have two tangents that intersect. Now, obviously, the picture looks a little strange because you think of a tangent as a full, complete line, okay, which it is most of the time. But we've got tangents going on here, and if I draw arrows, okay, these lines intersect like this. We don't have to envision it that way. We're going to focus on tangent segments today. Okay, so we're just going to focus on a tangent segment here and a tangent segment here, where two tangents intersect outside the circle. Two tangent segments have to be congruent. These two segments will always be congruent to each other. And so what that tells me is that the tangent equals the tangent. This is our formula. So you're going to get these word formulas that we use throughout this lesson to set up these problems. So in that specific case for this problem, that means segment AB is equal to segment CB and vice versa. Okay? The next relationship we want to look at is called a secant-secant relationship, okay? Secant-secant. I've got two secants here that intersect outside the circle. That's the important part. They intersect outside the circle. They consist then of two parts to each segment. There's a part outside and a part inside, okay? You need to understand, to find the whole amount that we use in this formula, you're going to add both parts of the segment. That means for each segment, the whole amount is equal to outside, not outside, outside plus inside, okay? Outside plus inside. So that outside times the whole amount, again, that's a sum usually, and this is a sum we're going to add to get those. Outside times whole of one of them is equal to outside times whole for the other one. So in that case, let's pick the top of these two secant segments. The outside is part A times the whole amount would be A plus B, outside plus inside. That product has to be equal to the parts of the other segment. So the outside part is C times the whole thing would be the outside plus the inside, D. Okay? That one's a little more complicated to work with, but it'll make sense when we do some practice problems. Okay, moving forward. We're going to take a look at chord-chord relationships. When I have two chords in a circle that intersect inside the circle, kind of we looked at this last time, we would have interior angles here. Well, we want to look at the segment relationships, okay? And that is very simple. Part times part equals part times part. Okay, so when we've got one segment part times its other part, that product would equal this segment part times its other part. So in that case, A times B for this specific problem would have to equal C times D. Okay, the parts that get multiplied are from the same segment. Okay, and finally, we have something called secant tangent, and that's kind of a combination of secants and tangents, where one of the lines or segments is a tangent, like this one, and the other one comes from a secant. So again, we've got a part outside and a part inside and the whole thing. So this is kind of a combination of those. It's really the same thing as outside times whole equals outside times whole, but here for that tangent segment, the whole is equal to the outside. The whole thing is the outside, which is why I end up doing outside times outside, because outside times whole means I can do outside times outside. So it's that outside squared. It's like outside times itself, but we just write it as squared, is equal to outside times whole of the other one. So in this case, the secant portion would have an outside part of B, and the whole thing would be B plus C. And then the tangent segment would be outside squared, so that would be A squared. Okay, so we're going to use these relationships. Okay, we're going to use these word equations to solve problems now. So the first thing we do is identify the segment theorem. These are your segment theorems. These words in bold are your segment theorems for each one of these. So as I look at number 1 here, these segments are chords. Both of these are chords. And so this is a chord theorem that I'm using. Chord is still right here. Part times part equals part times part. Okay, so I'm going to pick one segment and do part times part. So one part is X, the other part is 10. That is equal to the product of the other parts of the other segment. So 14 times 15. And then we just simplify and solve for X. 10 times X is 10X. 14 times 15 is 210. And then we divide by 10 there. And we get X is 21. Okay, simple enough. Let's move to the next one. Number 2, you'll see both these segments are secants. They have inside and outside parts. So this is a secant to a secant, or secant-secant theorem. Okay, the secant-secant theorem is outside times whole equals outside times whole. I'll abbreviate. Okay, so for one of the segments, we'll pick JL first, the top one. The outside portion is 10. The whole thing then is 42 plus 10. Okay. The other side comes from the other segment, NL. The outside portion is 13. The whole thing then would be 13 plus X. Okay, so we can simplify this quite a bit before we solve for X. On the left, do not distribute 10 to each of those. Don't do that. Let's simplify that number first. Let's do 42 plus 10 is 52. And then it's just 10 times 52, which is 520. Okay. But on the left, or I'm sorry, on the right side, we can distribute. In fact, we have to simplify that. Okay, so I'm going to do 13 times 13 is 169. And then 13 times X is 13X. So then we just subtract the 169 from both sides. Okay, 520 minus 169 is 351. And then we divide by 13. Okay, so 351 divided by 13 is 27. So X is 27, but this time they want something else. They want the length of NL. NL is the entire thing. It's the whole secant segment length. So if X was 27, I have to add those two, 27 plus 13, to get NL, and that's 40. Okay. So let's keep on practicing this. Let's go ahead and go to some other examples. Okay, looking at this one, you should recognize both these segments, AB and CB, are tangents. So this is a tangent theorem. Okay, tangent is the easiest one of these. Tangent equals tangent, meaning this segment equals this segment. Just set them equal to each other. 5x plus 23 has to equal 8x minus 19. And then we solve for x. Okay. Subtract 5x from both sides, you get 3x. Then add 19 to both sides, and you get 42 on the left equals 3x on the right. And then divide by 3. 42 divided by 3 is 14. But again, they want the length of CB. They want this one, so plug it back in. 8 times 14 minus 19. Okay, 8 times 14 is, sorry, let me go back a step. Eight times 14 is 112. Then I got to do minus 19, which gives me 93. Okay, so CB is 93. All right, let's keep going. And what we'll do is I'll help you set these up in this video, and then I'll probably have you pause the video to solve the equations yourself to save some time. On number 4 here, we have a segment theorem involving this bottom segment is a tangent. This other segment is a secant because it's got an inside and an outside part. So this is secant tangent. Okay, and that relationship is the outside times the whole thing for the tangent must, for the secant, outside times whole of the secant equals the tangent squared, or the outside squared of that tangent, okay? So the outside times whole side of this from the secant, there's the outside, 9 times the whole thing would be 9 plus 16, has to equal this tangent or outside part squared. When I do 3x squared, I can't just write it like that. I have to group all of that in parentheses. I have to square that entire thing. If you don't do that, you're going to get a wrong answer here. So now let's go ahead and add these together. 9 times 16, or sorry, 9 plus 16 is 25. And then 9 times that equals 3x squared on this side. If you remember your exponent rules, when I do 3x squared, it's 3x times 3x. Well, that's a 3 times 3, which is 9, times an x times x, which is x squared. Now, you notice I haven't multiplied these together. I could do that. I could get a big number and then divide by 9 again, because I got to get 9 by itself, or x by itself, right? So if I just divide by 9 here, before I put those together, I should recognize those cancel. So x squared equals 25. But that's not my answer. I need to know what x is. So we take the square root, and x is 5. Okay? Let's keep moving. If at any point the video goes too fast, pause it, replay it, do whatever you need to do to make sure you're getting this copy down. Okay? Number 5, this is another secant problem. What I would like for you to do is to pause the video here and go back and set up your equation for secant. Remember, that's outside times whole equals outside times whole. And then plug in these values and solve that equation for x, and then you can check your answer. If you need more time, keep the video paused. Otherwise, this is what you should get. X should equal 15 for this one. So there's the work. You can kind of take a look at that. Let's move on to the next one. Okay, here again, we have 2 chords that intersect. BD and AC are both chords. So there's a part times a part for each one. All right, this is the chord theorem. And again, that is part times part equals the other part times part. Okay, so one part, let's do segment AC first. One part is 6, the other part is 6. Then the other segment BD, one part is 4, and the other part is 5x minus 1, and you have to put that in parentheses. This is something that's going to mess you up if you don't. We want the part that is 4 times the entire other part, 5x minus 1, so you have to use parentheses. The left side here is 36, and then we can distribute here, giving us 20x minus 4. We add 4 to both sides, giving us 40 equals 20x. Divide by 20 on both sides, and x is 2. Now this time, they do want another length here. They want the full length of BD. Well, that means I'm going to plug in my 2 here for x, and then I'm also going to add 4 to it. Okay, I want to add those pieces together. So I'm going to do 5 times 2 minus 1 plus 4. It's 10 minus 1 plus 4. That's 9 plus 4 if you're doing it that way, which would give us 13. Okay? All right, a couple more examples here. Here again, we've got 2 tangent segments. All right. So that's a tangent-tangent rule, or tangent-tangent theorem. In that case, it's just tangent equals tangent, or part equals part. Okay, so one of the outside parts there, one of the tangents is 43 minus 2x. The other one is 12x plus 1. Okay, and so we need to solve this. What I would do, since you have this minus 2x, I would add 2x to both sides here. Okay, that gives you 14x here. And then we subtract 1 from both sides. And then we divide by 14. Okay, and so when you divide 42 by 14, you get x is 3. But again, it wants one of the segments. It wants wy. So we plug in here. 43 minus 2 times 3 would be 43 minus 6, which is 37. Okay. All right, one final problem. Again, on this one, I've got a secant, PM, and a tangent, LM. So this is secant tangent. All right. So that relationship, if you remember, secant tangent is outside times whole for the secant has to equal tangent squared for the tangent segment. All right. So the outside part of the secant is 8. The whole thing for the secant, we're going to add those together. So it's 5x minus 1 plus 8. That equals the tangent segment, this entire outside part, squared. All right, before I distribute, let's actually combine like terms here. -1 plus 8 is positive 7. And then I can go ahead and square that on the other side if I want. 16 squared is 256. Okay. And so 8 times 5x is 40x. And then 8 times 7 is 56. All right, then we subtract 56 from both sides. We get 40x equals 200. Okay. So then we're going to divide by 40 here on both sides, and x then is 5. But it wants the length of NP. Now, NP is not the entire thing, it's just the inside. So it's just that 5 times 5 minus 1. 5 times 5 is 25. 25 minus 1 is 24. There's 2 more examples here we're going to do. And these look a little different. On these, we're going to use a segment theorem again, but there's more than one thing going on here. But what you notice is all of these lines that make up these shapes are tangents, okay? So each tangent intersects outside the circle. So this is still the tangent-tangent theorem, all right? But the final result here is that we want the perimeter of this triangle, or the perimeter of this outside shape. Okay, we're going to use tangent, tangent. Remember, tangent, tangent just means each tangent segment is equal. So I'm going to actually kind of color code this for you. So we've got HE and IE that are equal to each other because they're each tangent segments. We also have FI and FG, or GI and IF, or sorry, GF and IF. Those are equal to each other because they're both tangent segments. And then we also have GD and HD that are equal to each other. So I'm just going to start filling in the things that would be equal to each other. So if HE is 16, IE is also 16 because tangent equals tangent. If GF and IF are the same, that means GF is also 9.5. And then DG and DH are the same, so DH is also 11. Okay, now I have enough to find the perimeter of the triangle. Okay, so remember, perimeter is just the sum of all the sides. Well, I've got 3 sides to this triangle. One side is DE, which is 11 plus 16. Remember, part plus part equals whole. So I'm going to add those together. 11 plus 16 would be 37. Okay, the other side is EF, which is 16 plus 9.5. Okay, if I add those together, that is 25.5. And then finally, I've got DF, which is 11 plus 9.5, which is 20.5 when I add those together. So I'm going to add all 3 sides now. 7 plus 25.5 plus 20.5 equals 83. Okay? So this is a little bit more complicated problem, but again, it's tangent, tangent, so all those tangent pieces are congruent. Number 10, similar idea here. Okay, on number 10, we've got pretty much the same setup, but now it's not a triangle around the circle, it's a quadrilateral. We're still using the tangent-tangent theorem. Okay, and if you want to abbreviate, you can. But now we've thrown in some variables. That's okay. We're still going to set this up the same way, and I'll kind of color code it again. Okay, we've got these points where the circle touches each tangent line. That's going to create these tangent segments that are congruent, and then these tangent segments are congruent. And these tangent segments that are congruent. And these that are congruent. Okay? So again, I'm going to start filling in all that I know. So since S to this point is 9, S to this other tangent point is also 9. Okay, these are equal to each other, so that's going to be where I set up my equation to find x. X plus 4 has to equal 5x minus 8. Let's go ahead and solve that. Subtract x from both sides. Add 8 to both sides. Okay, and then divide by 4. Okay, so if I divide by 4 here, 12 divided by 4 is 3. So x is 3. Now, I have to plug back in here because I want the overall perimeter, so I need these lengths. 3 plus 4 equals 7. So both of these are 7. Okay, so we're getting some progress. Now, these segments are the same. Now, it looks like I don't know anything about those. It just means I don't know anything yet. So let's jump ahead to these segments. Those are the same. Again, that's going to help me find y. So I've got another set of equations. Y plus 2 equals 3y minus 10. All right, so we subtract the y from both sides, then add the 10 to both sides. Okay, then we divide by 2. And so y is 6. Okay, but I want to plug that back in. 6 plus 2 equals 8. So both of these sides are 8. Now I can find these blue segments that I'm missing, here and here, because they tell you the entire segment from P to Q is 13. Remember, part plus part equals whole. So that 13 minus this 8 would give me 5. So that's that first segment there, so the other side is also 5. Now I can start adding my pieces together to get my perimeter. So there are 4 main sides I'm going to add together this time. Okay, let's do SP first. All right, sorry, I forgot to fill in some blanks. Y was 6, X was 3, and now I can find my perimeter. Okay, for that first big side SP, that's 9 plus 8, which is 17. And let's just keep going around the figure. This side I already know, that's 13, because they gave it to me. Then this side, QR, is 5 plus 7, that's 12. And then the final side, RS, is 7 plus 9, which is 16. So if I add these together, 17 plus 13 plus 12 plus 16, I get a perimeter of 58. And that finishes our examples for this lesson.